All right. Yeah, because I don't have a whole lot of time. So we'll just keep going. We'll call this second part, part 2. And so we've calculated all the numbers we need to actually do the join count analysis. So now what we need to do is open up the result. The data set, I called it the link table.dbf. So I'm going to open that guy up. And I'm just going to go ahead and delete one of these columns. I don't need both of them. Okay. I'm also going to go ahead and save this as I'm going to go ahead and save this as join count ms hispanic.xlr. All right, so I've got my, I'm going to create a new sheet. I'm going to put all the numbers that I need here. So I've got my observed black and white number, and we know that that's 194 divided by 2. I'll just write that. Okay, so we've got 97 black-white pairs. In other words, there are 97 boundaries where there's a high Hispanic population on one side and a low Hispanic population on the other. Okay, so now I need to calculate my expected black-white pair, the EBW. Okay, so in order to do that, I need to, well, let's create a few lines above this and create some of the other values that we need. Calculate some of the other values that we need. All right, so the number of joins is the number of common boundaries. So we can find that out. We already knew it. So this is the link table, right? Okay. So the link table says 400. So how many actual joins are there? Exactly. So it's 200 joins. So we'll just write 200 there. All right. The number of black values versus white values. In our case, that means, high, and then that means low. That number is, I set it. It's 41 both times. I just basically divided all the counties in half. Okay, so those numbers were 41. We know because we created them. I remember what that number was. Okay. All right, and then N is the total number of areas, black plus white. That's just the total number of counties in our case. So we'll put one more line in here. We'll put N counties. And then I'll say 82. All right. So now we have all the information we need to calculate the expected black-white value. So it's just 2 times, equals 2 times J times B times W divided by N times N minus 1. Make sure that we put ample parentheses in. That's what I always like to do. I think that'll be enough parentheses. So the numerator looks right. The denominator looks right. So that's the expected number of black-white pairs. Look at that number, 101. The observed number is 97. So right off, we can see that those numbers are pretty close. So even though I told you that this looks like, they're all next to each other, it doesn't necessarily mean they're clustered, especially when they're long and skinny like this, because we still have a lot of black-white pairs. If they're clustered, they're going to be all next to each other, and that would make it so that there was significantly less. So this number here would be a lot smaller if they were clustered, because we would have less of these. Sorry, not this number. The observed number would be smaller. The expected number is always going to be the same for the same data set. This number right here, the observed number, would be smaller. Can you see how that would be smaller if there was a cluster of let's say all of the high Hispanic population was just along the coast, then the only boundaries that they would share would be right here. Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is a lot less than 97. Right? So that would be a lot lower. On the other hand, we could get an even higher number of pairs if every other county was a different color. And then that would definitely be like a checkerboard pattern. My guess is this is going to be close to random. We do have a lot of counties. We have 82 counties. So it may still be significant. We may still be able to reject it. And if we did reject it, does this indicate that, just by looking at it, this is a short little quiz here, does this number being higher than this indicate, from what I just said, indicate that it's a little more clustered or a little more dispersed? This number being bigger.
Clustered? Wait, what do you mean? More clustered or dispersed
than random. So if they're the same, this is pretty close to random, okay? But on that scale, more clustered means that you have a smaller OBW than EBW. So this is a little bit more clustered, right? Like Ashley said, just slightly so, because this number is a little bit lower. And remember, like, think of the extreme example. The extreme example would be there's only 2 categories. Then they'd all be down here, and nobody would be up here. In that case, we'd have a very small boundary relative. Now we have a huge boundary. See how big this boundary is between? We have all that boundary. So that's why Ashley was right. 97 is slightly smaller. It's probably going to end up being pretty close to random. We'll see what the significance level is when we test it. But it's slightly on the clustered side, just a little bit. Okay? If the number was slightly over the EBW, it'd be on the dispersed side. But it's very close to being right in the middle. All right. The EBW is higher than the OBW. The OBW is less. It's clustered.
If it was less, then it's not clustered?
If the EBW is less, yeah, then it would not be clustered.
Okay.
So, but maybe I forgot the way I said it, but it's probably better to think of this number as being constant, because that number doesn't change based on the distribution of your values. This number does change. The OBW does change based on the distribution of your values. So well, it depends on which of these 2 numbers you're talking about. If the OBW is less than the EBW, it's more clustered. If the OBW is greater than the EBW, it's more dispersed. All right. Okay, so now we can calculate that big old number, and we do need the number. We need this table on the other page. So this represents the first column. It's pretty easy to get all the other columns. So this is the number of links, and then this is the L minus 1, which is just this minus 1. And so the way we did it, it's not possible to get a 0 here because we deleted all of the boundaries that don't share anything. But if you did have a polygon that didn't touch any other polygons, you could have a 0 here, which would mean you'd have a -1 here. You just want to get rid of that polygon. This is only the number of links. So by definition, you should not have any 0 values because that represents not a link. Okay, so this is L times L minus 1. And that's going to be equal to this times this. We fill down. And then this number right here is going to be the sum of that, and we do need that, equals the sum of L times L minus 1. $1,680. So now we have 1,680. Now we need to feed it into that big old formula of 15, 3. Okay, so it's quite a large formula. I'm going to divide it up into the numerator and the denominator because that'll make it easier. So I will call this the standard error numerator and the standard error denominator. Okay, so the numerator is the square root of the EBW plus the sum of the L times, yeah, we got that, equals plus this value. See, I can get it off of another sheet. Times the black, number of black, times the number of white. I'm going to put all this in a parenthesis because it's going to be divided by n times, another parenthesis, n minus 1. So what we're doing there is saying that, and then we'll go one more. Yep. So that should be the whole numerator. Hopefully I got that right. I didn't. Yeah. Oh wait, this says sheet 1. That's not right. Okay. Why does this always say sheet 1, B3? Oh yeah, that is sheet 1. B7. Where's B7? B7, 1012384. That's right. Plus, oh, that's my problem. Okay. So it's B7 plus, I have a parenthesis, sheet 1 D85. That's the one where it should be getting it from here. That's not sheet 1. That's some linked table. Hopefully that's getting that number from. One thing I could do is, let's clean this up just a little bit. I'm going to say L, sum L. I'm going to put that number. Okay. All right. I'll just retype this so that it makes a little bit more sense. Okay. B8 plus, now I've got that number right here. I got it right there. Times B times W. That's my, that's the small numerator in there. Okay. Divided by N times N minus 1. I want to make sure it does that before. Where's that one coming from? Yep. All right, that looks good. It probably won't do this plus before, but I'm going to put another set of parentheses in there. So I got the same number. But that formula looks shorter than referring to the other page. but that's the formula. So I just put that sum L times. It's really the sum of L times L minus 1. All right, so that's my denominator, my numerator. And my denominator is going to be a little bit smaller, a little bit larger. It's not a square rooted though, so just got a big old formula. 4 times j times j minus 1. I'm going to put that in parentheses. Actually, this whole thing has got to be in parentheses. All right, there we go. Okay, minus the sum of this big old guy, which is that. Yep, okay. And then that can all be escaped out of the parenthesis times b times b minus 1. Okay. So this is where automation would help. Times w times w minus 1 in parentheses let's see if that looks right. W minus 1, B minus 1, L 4. I think that's right. Oh, that's a plus sign. That's not a denominator even. So in formula 15.3, this all gets added, not. So that's like a new line. Not divided by. Sorry, I misread that. So these aren't really numerators and denominators. This is just standard error. I'm actually dividing this up into 3 pieces. Standard error 1, standard error 2, and then finally standard error 3. Okay, so now I'm going to do the bottom of that. N equals n times n minus 1 times n minus 2 times n minus 3, and then what's that number? Equals, now we got a really big numerator and a really big denominator, equals that divided by this, and then we say equals this minus the expected value. Right? So the standard error is going to be this. The whole standard error is going to be this plus. Actually, I probably got an order of operations problem. So let's call this standard error 2. This is just an intermediate value. Okay, so this is the first term right here, and then it's added to this term. Okay, this term right here. Added to that term, and then we subtract the EWB. So we'll put that all in one formula. This plus this minus the square of this times this. And we get negative 455,717. Something wrong, because that should not be a negative value. Well, let's see what the value would be if we now get the expected minus the observed divided by this value. I wonder why we get a divide by 0 here. Oh.
That should be a negative.
What's that?
It should be a negative divided by a negative, right? Observed minus expected is going to be negative.
It is. Observed minus expected is a negative value. But this is observed minus expected divided by this, which is a negative value, which makes that positive.
So you should still be able to take the square root of that, because divide a negative by a negative. So,
Well, where do I need to take the square root?
so
I have the square root already. Oh, but this is all square rooted.
yeah, all in the root of the square root.
So do you add this to this to this to this, and then take the square root?
So, yeah, it's like this plus this.
What's that?
Minus this.
I messed up. Yeah, I was confused.
Yeah, actually all of that is under the square root.
So
It's like nothing to say.
And what is this minus? Does that mean it's divided or?
I'm going to take the square root out of here.
It makes it look like it's divided.
So this plus this all in here.
Okay, makes a little more sense. All right. Okay, so I do have a slide of this, so let's look back at that real quick. Okay, so this is what Ashley and Kate are talking about. So on this formula here, we've got this square root symbol, and it just keeps continuing going. So really, there's one, two, three, 4 terms in that you just add together. Well, this one you subtract, and then you take the square root of the entire thing. Okay. So what I've labeled standard error 1 is actually the first 2 terms here. Okay. And then what I've labeled the numerator and denominator are these numerator and denominator for the third term. So I could just go like this divided by this, and this is SE2. And then finally, SE3 is the square of this times, whoops. Okay, so now I just take the first 2 terms and subtract the third, equals this plus this minus that, and take the square root of that. And that's the number that I need here. And that is much more normal. And that's the value, close to the value I expect. Okay? I think that's right. Thanks for pointing that out, actually.
So that's the Z value, right?
This is the Z value that we can look up in the T table. In the Z table. Since it's a Z table, the degrees of freedom doesn't matter because the Z table is the same for everybody. So negative 6.1275 0.61. The closest one we got is negative 6.1, which is 2291. So that's 0.2291. We subtract that from 5. So we've got a p-value of 0.27. which this would actually only be the one-tailed p-value. So if we doubled that, in either case, though, it's nowhere near 0.05. So even though it's slightly clustered, it's not significant. What's that? Well, it's one-tailed because the book reports one-tailed.
Oh,
So this value right here, if you look, it only reports. This is the area under the curve between the middle of the distribution out to one tail. That's what this is. And then so this is the p-value because it's 0.5 minus that. And then our p-value for a two-tailed is actually doubling that. So there's all basically, if this represents a random distribution, there's almost no chance that it represents a random distribution. So that's the value, 0.2. That's the p-value that would report. So in that case, we would definitely not reject that null hypothesis. So the observed number of black and white joins is equal to the expected number of black and white joins in a purely random pattern. All right. So I talked about writing a script, but also if you just save this spreadsheet out, then really this would be an easy process the next time to do this, because all you have to do is stick in the numbers for the joins. You just need 1, 2, 3, 4, 5 numbers, and you can calculate the rest of this. Okay? So we can kind of play with this. I'm going to save this and then revert back. But let's say that we only had, and really this could happen, let's just say we only had 40 black and white joins, observed black and white joins. Oh, then, well, it would be nice, actually we could do equals, returns a normal distribution for the mean and the standard deviation. No. Yeah, there's not a way to get that, but that would, anyway, whoops. Let's say we had this 40. Look at the Z, look at how much it affects. Like if there were only 40 black and white joins, in other words, it'd be more clustered, then this number goes all the way out to negative 8.86, which is almost certain. I mean, if you look at the Z table, it's definitely significant. In fact, anything over three standard deviations is going to definitely be significant. So even a value of 70 or 80 would be right on the cusp. 80 would be just barely significant and cause us to reject the null hypothesis. Okay, so we've got a value of 97. But that's in the accept range. Now going the other direction, if we had a value of 120, in other words, there were 120 black and white connections, we would be on the cusp of the dispersed side of the equation. We're not quite there, but 125 would definitely push us into being dispersed, for sure. So there are 125 of these boundaries that were different. Okay, that would probably take more, close to half of them being a bunch here. Like what if that one and that one and that one were also? Then we have a bunch more boundaries that would pop up. All right, but playing with that number kind of shows us how it could change. I'm going to change it back to 97, and I'll upload this. Okay, so you can kind of see how it operates on that continuum now. It took us a little while to work through that formula, but we did it. Okay, I actually remember when I taught this class 2 years ago. Now I'm having deja vu. Same problem working through the formula in class. Okay. All right. So it kind of just shows how you can use numbers to assess and answer a question like that. All right, now, oops, I don't think I actually want to start it up. Okay, so Talked about that. So let's go on to a couple of these other statistics that are even more involved in terms of their calculation, but they're useful. They're already in our GIS, probably because they're so involved, and somebody thought, why don't I make a script to do this? But these are Moran's I, which is in the book, and then GHY, which is not in the book, but I still put it in the slide presentation, and it's also in our GIS. So the way that these basically work is looking at so another thing that makes these more computationally intensive is that we can actually do it on not just yes or no values, not just categories, but numbers themselves. So we can say, oh, this is a cluster of high values. So we can have a value like rate. Like we could have instead of just saying Hispanic yes no, we could say we could actually use the column that represents. I think I still have that, or did I get rid of it? Yeah, no, I still have it. We can actually use that new column I made that has the Hispanic ratio. In other words, the ratio of Hispanic to the general population. Okay. So we could use that instead of using the high-low values. It is good to often use rates or ratios, although you wouldn't necessarily have to, but most of the time, just think about it, particularly with socioeconomic data, you're going to want to use a rate rather than just because people are clustered. All right. So what it does is it operates by taking the weighted cross-product deviation values for contiguous pairs, and they're multiplied together and summed. Okay? So what that means is that we're looking at the attribute value and its neighbor. And how we define neighbor is different, but in this case, it can be different. It can be lots of different things. But the way we're going to define it for the next few slides is the same. A neighbor shares a common boundary. Does that make sense? So, so these values where we're comparing a neighbor to its neighbor, that's the value of contiguous pairs. So if my neighbor has a value of, let's say, 15% Hispanic, and this one next to it has a value of 20% Hispanic, the difference between those is 5%, or 5%. The difference between those two values is 5. And that's the value that we're looking at. We're summing up all those cross-product pairs. Okay? So if we have a lot of values that are positive, that indicates that we have a clustered relationship. Negative represents what we had first. It's kind of the opposite of what we just did. But I is going to range from -1 to 1. So with Moran's I, no spatial autocorrelation data, that represents that they're completely random, and that's the null hypothesis. So this is a measure of spatial autocorrelation. And we're defining spatial autocorrelation as a neighbor, a value next door. All right. So if the p-value is significant, obviously reject null hypothesis. Okay, so the way this works is actually related a lot to next week. Next week we're going to start talking about relationships like this. Okay? And next week's actually a little bit easier concept to think about in your head than this week. This week, the x-axis here is your variable that you're mapping, in our case, the percent Hispanic. The y variable, which is, in this case, I just wrote w_prime, it's basically it's the value of your neighbors. So this dot represents the value of one value, compared to its neighbor. Okay? And so you have a dot on here for every join that Remember we talked about joins last week? You have a dot on here for every link, you have a dot. So for every link, you'll have a dot. And if you think about this quadrant, these quadrants here, if you have a relationship, it shows that there's what? That nearby values are close to other nearby values. If you don't have if you have a lot of points all over, it shows that there's not necessarily a relationship. However, if you have a lot of dots up here, then you have a lot of nearby values that are similar, that are high. You have a lot of values down here, you have a lot of nearby values that are similar but they're low. And then here represents values that are different from each other even though they're nearby. All right, so we'll talk about regression next week, but really Moran's I is the slope of this regression curve. How tight and related these values get to each other. Okay? All right, let's go ahead and calculate Moran's I really quickly on our data because it's already pulled up and it won't be hard to do. So here is the Hispanic population. I'm going to clear selection, clear selective features. And this is really easy. It's already built into our GIS. You just hit it. It's under the spatial statistics tool, and it's called spatial autocorrelation, Moran's I. Double click on it, and you choose the feature class. In our case, we want to do the Mississippi. And the field that we want to do is this time we want to do the Hispanic ratio. And we always want to check generate report because it'll give us the p-value and all that stuff. All right. Now, this is where it gets a little bit, like, the book doesn't talk about this. All right. So this conceptualization of spatial relationships, your book just says your neighbor is the one next to you. And that option is there. So this one right here is contiguity edges only. This is the formula that's in your book. So it's going to go ahead and calculate the formula in the book if you choose contiguity edges only. So that is, that's the one you should choose for the homework for Connecticut. Because I told you not to calculate it by hand, just use this thing. Contiguity edges only is the one that's in the book. What it's saying is a spatial relationship is defined by those polygons that touch your polygon. All right, now if you choose inverse distance or inverse distance squared, what you're doing is it's going to calculate the distance to all the other polygons, and it's going to say a weight is defined by the inverse of the distance. So closer polygons are going to receive a higher weight. So what's a weight? Well, if we're doing the contiguity edges only, whenever two touch, it gets a weight of 1. It gets put into the value as a 1. If they don't touch at all, the values are never used because the weight is 0, and when we multiply everything by 0, we get 0. Okay? But think about it. If we use inverse distance, if the distance is 10 versus 20, the weight's going to be half it's going to be twice as big in the one that's only 10 away as the one that's 20 away. But it's still going to be considered a neighbor. Okay. So if you have a reason to calculate Moran's I and you could think, well, I'm kind of interested in the fact, like, what if a cluster could be represented, and I didn't care if there were a few polygons in between that were low, but I still wanted to call it a cluster if they were nearby each other, even if they don't touch. Then you would want to choose one of these. Okay? And then if not, if you decide to have touch, you could choose one of these. The only difference between these two is it puts the weight at 1 if they touch at a corner, if you choose corners. If you choose edges only, it only counts as a weight if they touch. So they only count it as a neighbor if they have a common line boundary. Edges means point or line boundary. Finally, you could put get spatial weights file. If you choose this one, it ignores your spatial data altogether. And you have to come up with a relationship between every area, how much weight it should have. So you could, okay. One example of where I've seen that is, let's say you're interested in stream flow, okay? And you're interested in a cluster on a stream. Is the stream have a clustered values as you go downstream? What you could do is make it so that the weights only matter going downstream, but not upstream. And the weights could get progressively less as you go downstream. Like immediately downstream could have a higher weight than 10 meters downstream, or 20 meters downstream, or 30 meters downstream. But you wouldn't have the weights going at all upstream, because nothing is going, assuming that this is something that doesn't swim against the current, it wouldn't go upstream at all. So that's one reason why you might use that. Okay, so that's that. So we're just going to do this MS. We're going to choose edges only, and the field is going to be the Hispanic field, the HR. All right. Okay, the standardization doesn't really matter a whole lot when you're doing contiguity, because it's just 1 or 0. But you might experiment with that if you were doing it. Do I have an output feature class? I need to generate the report. There you go. Okay, so I'm going to run this through, and we're going to see what the value is. Geoprocessing, results, summary stats. No, we don't have much time here. Oops. Report file, copy, open up Explorer, and paste it. All right? So, this nice little report tells us that the z-score was 1.70. So now all of a sudden we're out there. Look where it is. It's in the slightly clustered region, which we decided that was the same case with our joint pattern analysis. But let's look at the p-value. The p-value is 0.80. The p-value is a lot different. 0.0879. Okay, so we're a little bit closer to significant than we were with. Well, we're a lot closer to significant than we were with the joint pattern analysis. So, using a 10% cutoff, we would definitely be in the significant region. There's a 10% likelihood that clustered pattern could result from random chance. I think I actually like this slightly better, because it is kind of obvious. Well, not obvious, but you could see that there's a clustered pattern here. It's not a very strong clustered pattern, but there are some clusters, but they're long and skinny. So this is a value that we get. All right, but it's clustered either way. It's just significant at the 0.10 level, but not the 0.05 level. All right. Okay. So here's a few other examples. Here's Puerto Rico population density. We get a Moran's eye of 0.49 there. Okay, indicating that it's clustered. Okay. All right. Now here is the Gary's C value. It's similar to Moran's eye, but it's not in the book. It's actually on a different scale from 0 to 1, and 0 represents positive autocorrelation, 2 negative autocorrelation, and a 1 is that we don't have any autocorrelation. If you wanted it to go on a scale from -1 to +1, you could. You just stick it in a formula, subtract 1 from the value. Okay, this value is here. Okay, it's I guess C isn't there. Okay, but a very similar one here is this, the high-low clustering, Getty's ordinal G. So we could It's very similar. I have a slide on it in a second. So we could do the, oops, I didn't mean to do that. The HR field, generate report. We want to still do edges only. Say OK. So it's got the same exact inputs. We go back over here. Okay, we get a result that indicates that there's not a lot of clustering. It's mostly random using the GHY. Now we haven't talked about this yet. Okay. All right. Ooh. So just like with the join count, there is a non-free and a free sampling method. Okay. So now we're going to talk about the GHY here. So the GHY is different than Moran's and Gary C because they don't distinguish between clusters. They just say whether or not there are clusters or whether it's dispersed. So these other statistics that we're going to talk about now actually talk about hotspots and cold spots. A hotspot are clustered high values, and low spots are clustered low values. That's what a hotspot and a low spot is. So here's the global G statistic, the one I just ran. It distinguishes between hotspots and cold spots. And if it's significant, it's saying that you do have high values that are clustered together and low values that are clustered together. Okay? If it's not significant, your high and your low values are random throughout the area. So it's a little bit different than saying is there clustering or is there not clustering. It's saying are those high areas and low areas clustered. Okay? All right. So if it's larger than expected, you've got hot spots. If it's smaller than expected, you've got cold spots. And if it's right in between, then it's random. All right, so that's the one I just ran here. That's this one right here, this report. So it's looking between high clusters and low clusters, and you're right in the middle, which makes sense if you look back here. Okay, we've got some high clusters and some low clusters. We're right in the middle. All right. All right, we're not going to go through. The book doesn't even talk about it, but I've got it in a slide. Okay. All right. So the one thing about the general G statistic is that it doesn't show negative and positive autocorrelation. Okay. Another thing is, I've said up to this point, you really should be using ratio normalized data. In other words, normalized data. With the general G, that's a rule. Only use it for a scaled value which have a natural zero. So rates is the best type of data to use it for. And like the other ones, you can use any type of spatial weight matrix. We've been using the contiguity ones. ArcGIS gives multiple options there. Here's running it on some data in some crime data for Ohio. Okay. So in this case, it was significant. In other words, what it tells us is that the high crime areas are significant. There's a lot of high crime areas that are clustered. There's not a lot of low crime areas that are clustered. They're more dispersed. All right. And then your final thing that we're going to talk about is this Moran's local. And your book even says the math here is beyond the scope of the course. So we're not going to do the math. We're going to talk about how to interpret these local measures. What we've done up to this point, we get one number for the whole study area. That's called a global measure. What we're going to talk about for the rest of the class here are these local measures. Local measures means that a value is calculated for each unit rather than for the entire area. And so it shows us where those clusters are. So oftentimes we run these in steps. We first run a global analysis, and then we look at those hotspots through these local indicators of spatial association. Lots of the literature refers to this as LISA. Okay? Local indicators of spatial association. And in fact, it's right here in ArcGIS. The local Moran's eye, the one we're talking about right here. And there's also a local GETA statistic, a hotspot analysis. Okay, so the goal here is to identify local clusters and to identify spatial outliers, things that are different. So when we run a local indication of spatial association, positive values indicate that there are similar levels in adjacent, in our case, counties. Negative values means that there are dissimilar values, and these values are assigned to each county. Okay. So each aerial unit gets a new value in this analysis, whereas what we talked about earlier, only the whole area gets a value, gets a test statistic and a p-value. Now each individual area gets one. Okay. Each polygon. So we start off, here we have literacy rates. We take the literacy rates and we classify them. Here's the local Moran's eye value. And then this is whether or not the cluster was significant or not significant. So we can take these values and say whether or not they were significant. We can see high cluster areas and low cluster areas. We'll look at the type of the relationship. Okay. So these are literacy rates. These are the low literacy areas. These are the high literacy areas. What this ends up showing us is that this county right here, not county, province in China, that has a high value. In other words, its neighbors are also high. This is a low cluster. In other words, what it's saying is the neighbors of these counties have low values or provinces. All right, let's run this. Well, before I run this, so basically what we're doing is we're dividing the scatter plot up into 4, and the areas that are really high and the areas that are really low show up on the map. All right, here I'll run it for this. The local on the Hispanic. And I'll choose GHY column. We're still just going to use edges only. Yep. Okay. All right, there's the results. So what this is telling us, if we open up the clusters here, is that there aren't any clusters of low-high. Okay, so the significant clusters are all high-lows or high-high clusters. In other words, these are counties that have neighboring counties that are also relatively high in their Hispanic ratio. These counties are counties where their neighbors are relatively low in terms of the ratio. They're high, but their neighbors are low. These guys are high, but their neighbors are also high. That's the way that we read that map. Let's see if we can run this real quick. I don't have any other ratios. Let's see if there's anything else that makes sense, though. Well, I'm sure that some of these populations are.
Do you have population density in here?
I have population density? No, do I?
Yeah.
It does not look like I do. I mean, the population divided by the area I'm just going to run this real quick. So we'll look at, oh, is it going to write over it? Nope. So again, even for this analysis, and this one's not quite as good because we're not using a rate, which I said you should. But these counties have a high value, a high number, and this is just a raw count of the African American population, and their neighbors do too in those counties. But there aren't any other high clusters, in the high clusters in the state, or really low high clusters in the state. Okay, so this example is actually a little more interesting because it has things on both sides of the scale. You can see where those clusters exist. Now this thing still generates a report, or maybe I didn't ask for the report, or maybe I'm thinking of. I'm actually thinking of the hotspot analysis. That generates a report. Okay, it doesn't generate a report, but this thing does generate the, it does generate the contiguity value of the data set. So there we've got a high there, another high. We could map just the index or the score. The score would probably be better to. Let's change this to quantities and score. So they want you to interpret that other one, but this one does show the score. And you can see these counties in here have the highest scores. They're way higher than any of the negative scores. The negative scores, they go down to 1.5. That's why they didn't show up as significant. But these are in standard deviations. The numbers here. So this is saying that its neighbors are way different than most of the typical neighborhood by a lot. This is saying that its neighbors are low, but they're not significantly so. They're not outside of that 3 standard deviation cutoff. That's why they didn't show up. But if you did have these z-scores get way out into the negatives, then they would show up a little. So this map basically shows you in our case the yellow areas. Let's also do this one. Quantities, z-score. So in this case, the yellow areas. This is Hispanic. The yellow areas mean that your neighbors are about the same as everybody else's neighbors, and there's kind of an even mix. The red areas mean that your neighbors are high like you. The blue areas mean that your neighbors are low like you. Okay. All right. So that's it on China. So we've got 4 quadrants. The way to think about this is that I'm similar to my neighbors, or I'm different than my neighbors. Going this way means that you're different. Going this way, you're similar. If you both have, actually the colors should be the reverse, right? Sorry. So these quadrants mean that you are similar. These quadrants mean you're different. That's what I said before. I changed it. These mean that you're different from my neighbors. That's low, high, high, low, high, low, low. Here's medium income in Denver, Colorado, or sorry, Dallas-Fort Worth. That's from their study. You can see these low clusters of low income areas nearby other clusters of low income areas, clusters of high income areas near other high income areas. So what might be more interesting here are the high-low clusters. So this is a high nearby lots of lows. And in this case, they didn't just use common boundaries; they used distance. there's another high cluster right in the middle of lows. But it has the ability to pull out those things that might be interesting. In this case, the kind of cross products are the more interesting. There's a cluster of low area in the middle of a high area. Medium income in Ohio. Okay. And then you've got this local get us ORD statistic, which is similar in its purpose. You can run that to kind of finish off class here. Here's Mississippi using the Hispanic population, saying that it's contiguity, and saying okay. So when this runs, it's showing the hot spots and the cold spots. So these are hot spots, these are cold spots. In other words, areas where there's less clusters of low Hispanic population and clusters of high Hispanic population. So each of these analyses tell you slightly different things. So think about it this way. We'll start with the global operations. So the joint count analysis is kind of its own thing, and it's looking at just yes, no's, black, white, high Hispanic, low Hispanic. Okay. The other ones we talked about later, there's basically 4 of them. Okay, so there's Moran's I, and Moran's I tells us about spatial autocorrelation, whether or not things are clustered or dispersed. Okay, then we've got this global G, which isn't in the book, but the global G tells us if our clusters are mostly high values or low values, or if there's an even amount of both. So that's the global G statistic. Okay, that's this one right here. The general, they call it general G in RTIS. Make it sound like this. Okay, so then we've got these 2 local ones, and they tell us something slightly different. The local ANSLAM, the local Moran's I, which are these 2, tell us basically they divide this space up into 4 different things: the high clusters, the low clusters, and then the mixed clusters. So that can be good analysis for trying to determine if there are little pockets of values and where they are. And then we could do further analysis of those areas. Okay, and then finally there's this one, which is also not in the book, the get us G hotspot analysis that shows us where the high and the low hotspots are. And these will change. This is the way I just ran it with contiguity, but you could run it again using distance. I don't know if this will change too much, but let's try it one more time. Mississippi, Hispanic, ratio. Let's just do inverse distance. And see if this will change at all. So we get a little bit a different map. Okay. We're less confident in some of those cold spots than we were when we're just using the contiguity neighbors. Because now all of a sudden there are areas further away that are being considered, and they're more random. There's not as much of a spot unless we're just considering our neighbors and ignoring the things that are just beyond our neighbors. All right. So anyway, let's just talking about how to run it in ArcGIS. So before we end, let's just talk about the homework real quick. I just want to make sure everybody understands. This is the homework. I do have this data set loaded up in ArcGIS. So you can download it. And you can do this on the computer like I did it, but you have to calculate the join count analysis. And so you basically have to calculate those numbers that I talked about in order to get this number. So that's probably going to be your biggest headache. But if I put up that Excel spreadsheet, it won't be a super big headache because you can just put the new numbers in and get the new z-score. All right. Now this one though, I wrote up online the values that that you don't have to do. I mean, sorry, I put up online that you don't actually have to calculate those values. For Moran's I, just run it in ArcGIS. Don't calculate all these values out.
Oh,
Just calculate it. Still answer the question. State null hypothesis. You don't have to calculate the join count. You do calculate the join count statistic, but that's from the last question in Connecticut. And so here you can pull these values out of the report that it generates. Well, really, you don't necessarily need to pull out this value, but you'll get this value in the report. You'll get the z value in the report. You pull those values out of the report. And then, if I was in this class, you don't have to turn this in, but you could experiment a little bit running Moran's I in for various county level data or any other data that you have, and kind of look at the results. All right, that's it. So I'm gonna stop the recording.